Welcome to this presentation of Ariane, a low interaction framework for privacy preserving deep learning using functional secret sharing. This is a joint work with Pierre Tologna, David Pencheval, and Francis Bach, and it was done at ENS and INRIA. So, what is the context here? The objective is to investigate new algorithms for private evaluation, but also training of real-world deep learning neural networks. We will focus on additive secret sharing, and I will give you like a small reminder of how it works. So say you have Alice and Bob that have their private inputs, so 7 and 3, and they want to do some computation, maybe the addition on this input without revealing them. So first they build secret shares of these inputs. So here it's simple numbers for the sake of arithmetic, but it should be completely random numbers in huge space. They distribute their shares across the different parties, and then they are able to interact and compute over the shares to do some computation. So here, for the case of addition, they only need to add locally the shares, and they build new shares that happen to be the private shares of the result of 7 plus 3. So this is what we call secret sharing, because no second party can reconstruct alone sensitive data because the shares are completely random. And a cool feature about additive secret sharing is shared governance, which means that data can only be used or decrypted if everyone or a sufficient subset of the parties agrees to do so. And so back to our use case of machine learning, data and models can also be secret shared exactly in the same way. If you take data may be like a picture is composed of pixels, and these pixels can just be secret shared, and the same for neural networks, which are just composed of parameters that can also be secret shared. So what operations are needed to do private machine learning? We need addition, and we have already seen how to do this. We also need multiplication and matrix multiplication. This is actually not very difficult, in the sense that the only difference is that we will require now a third party that we call the cryptographic provider that will provide some cryptographic primitives for the computation, and one extra round of interaction between the parties will be needed. The most challenging part here is the comparison. Comparisons are widely used for the ReLU activation functions that we have in neural networks. There were already a long line of work around how to compute some efficiently the comparison in MPC, but most of these techniques actually rely on a quite important number of rounds of communication, and this is what we are trying to investigate here. So say we have this function f that we want to compute on an input x. For example, it can be comparison to a threshold, so 0 if we want to do the ReLU activation function. When we are in classic additive secret sharing, what we do is we have our secret shared input x, and we will apply a public protocol which will be applied by each party in order to output secret shares of the result. In functional secret sharing, it's actually the other way around. It's supposed to have a public input and private protocols that we call function shares. So in this case, the function shares could be still a comparison, but a comparison to an unknown threshold alpha. And then each party will use the function shares on the public input to compute private results that will actually sum up with the original value. So to get to this framework, we actually, as we have secret shared inputs, so here's the y input, what we do is we resort to masking. A private and secret shared mask alpha is also provided by the crypto provider alongside the function shares, and this allows to publicly reveal x, which is So y plus alpha, where alpha is a completely random mask, and because the crypto provider has chosen the mask alpha, it can make sure that the threshold in the function shares is also alpha. So what we do at the end is that we are computing x compared to alpha, which is equivalent for real numbers to having y compared to 0. So the protocols actually relies on bit decomposition and bit per bit comparison. Because x is public, it's very easy to compute the bit decomposition of x. And for alpha, because it's chosen by the crypto provider is also able to compute this bit decomposition. So the bit per bit parity comparison actually spans a binary tree, which I've shown here for only for any quality 3 bits, but in practice we will rather use 32 bits. And goes this way: we start by the most significant bit, and so that's our x1. And say now that x1 is bigger than alpha 1. So we go on the right hand side of the part of the tree, and we know that whatever happens next, the output of the comparison will be false. Here alpha is represented on this red line here. So maybe we will now compare the second bit. Say that x2 is strictly smaller than alpha 2, so we are on the left side of the tree, and we know that no matter what happens next, the result of the comparison will be true. And if now the 2 bits are equal, we need to go to the next part to decide whether the computation is true or false. So this is the spirit of the implementation of our protocol. This protocol achieves honest but curious security. It's a 2-party computation protocol, and it relies on a trusted dealer. It actually has a small error rate because of edge effects, but it can be avoided with extra computation. And actually there was also a follow-up work that I've shown how to have a similar protocol but without this error. But actually, as we show in our experiment, it does not affect the accuracy of our models. So why did we choose function secret sharing for private machine learning? The first reason is that it is part of the family of multi-party computation protocols that only rely on very lightweight cryptographic primitives. Actually, all we need to do is to compute AES. So this allowed us to provide an implementation on the GPU, which is also very important for machine learning practitioners. And most importantly, it reduces considerably the number of rounds of communication compared to other protocols like SecureNN, for example, that we have shown, because we only need one communication round for private comparison. And in addition, this round is very efficient in terms of the number of information that we transmit. It is of the size of the input. The drawback is actually the size of the pre-processing keys, these function shares that we have shown. For a ResNet model taking as input a 200 by 200 pixel image, the keys can be as heavy as 2 gigabytes. It means that it can be really tricky to store all these keys in advance. So here's the result we got for doing private training on small models like LeNet on MNIST, and what we show is that in a couple of hours we'd get the same accuracy than if it was trained on plain text. We were able to do private evaluation on bigger models like VGG16 or ResNet 18. We see that we get inference in a couple of seconds, and we can even improve this result with our GPU implementation. So that's quite interesting because it means that we can it can match real scenarios where we can only wait for a couple of seconds to get the result. And this is actually what we did in another study when we were doing end-to-end privacy preserving deep learning on medical imaging. So we had a task which was to detect if an image would be viral, bacteria, or normal, and functional secret sharing. So Ariane was used here as secure inference as a service, and that's very interesting because it's a private evaluation of a Resident 18 that had expert level accuracy on this task. And in this scenario, latency matters because the practitioner is waiting for the response, and we are not always able to provide batching as we do in our and also in other many results where we provide a batch result of our inference time, which allows to amortize the cost of communication. And because we are quite efficient with our single round of communication and functional secret sharing, here we can gain a real advantage. A few remarks. So we are only in the honest but curious security setting. That would be like an interesting part to work on, and also it means that the model is not visible at all during training. And this is very interesting because that's a condition that we need for some differential privacy algorithm, like the one based on Lagrange diffusion, and which suggests that we can expect powerful combination of techniques like functional secret sharing with, for example, differential privacy. If you want to hear more about functional secret sharing, tomorrow there is a session with two other work, Pika and LLMA, that rely on this work and provide some very interesting extension and alongside nice benchmark. So thank you very much, and I'm happy to take any question.